All right, here we go, picking back up where we left off. This in front of us is the overall plan for the remainder of the lecture, which is the whole reason why we're here in the first place, learning how to interpret 12 leads. We're going to walk through rate, we're going to walk through rhythm. The section that we're doing now is going to have a lot of focus on axis. We're going to figure out the general vector that the electricity is flowing through the heart. Additional things, we'll talk about Wolff-Parkinson's-White. We'll have a whole section on hypertrophy for your bundle branch blocks. On finding left and right atrial or ventricular hypertrophy. The wide QRS is going to be our bundle branch block discussion. And of course, everyone's favorite, step number 7 is going to be ischemia and infarction. I realize MIs are super exciting, but we're going to try and keep that to the latter half because everything that comes before it does have great value. And then last but not least, we always need to correlate symptoms with what our tests are showing and then putting together a final diagnosis. So without further ado, rate. You guys know how to calculate rate from basic arrhythmia. There's the easy method, which is taking the total number of R waves in a 6-second strip and multiplying by 10, giving you a nice round healthy number. The next best one, which is one of my personal favorites, is going to be the 300 method or the count method, where you start at one of the large boxes and you just skip from each large box to the next, and your patient has whatever QRS rhythm, well, from here to here, 300, 150, 100. So in the one that I just drew, this patient's heart rate roughly is between 100 and 150. Last but not least is the most accurate, and the one that would be ideal if everyone would do, and that is counting the total number of small boxes between 2 R waves and dividing into 1500. So, 1500 divided by 9 or something like that. Next step's rhythm. Again, this is basic arrhythmia type stuff. Please use the 2 lead that's at the bottom of the 12 lead EKG. That'll be your best bet to go through there and figure out if it's a fib or flutter. Decide if they're PVCs versus PACs, stuff like that. So your rhythm, you're going to determine fib, flutter, junctional, all that kind of stuff based on that long strip at the bottom. All right, the big thing, axis determination. This is not a simple topic. It's a little bit challenging to go through, but I'll try and bring you along. The ultimate idea is this. We are looking for the true mean QRS. In every 12 lead, at least one of those is representative of the mean QRS, and it's our job to find it. And so this whole process I'm going to walk you through now is how we get there. This is what we really want to focus on, and it's this. The mean QRS is any one of those 12 leads. The lead axis is another item. So think of it this way. If you find the mean QRS, it is a fact that any lead that is perpendicular to the mean QRS will have a biphasic QRS. So let's take a look at this to kind of put it into better words or make more sense out of it. Right here we have just some generic deflections based on their relationship to one another. if we, for argument's sake, well, actually we'll walk it this way. Actually, I'm going to go with a different shade of green. Sorry. Assuming that this lead across the bottom here is our mean QRS, it is then guaranteed that you will have a perpendicular lead to that one. And that perpendicular lead will have this type of QRS, which is known as, you can call it equiphasic if you want, but isoelectric is what I prefer to call it. And this isoelectric lead is perpendicular to the mean QRS. I know I keep saying the same things over and over again, but there's a reason for that. If I look at any person's 12-lead EKG and I can find this one right here, I then know for a fact that whatever lead is running perpendicular to this one is going to be my mean QRS. And then there's a few other little things we can do to determine exactly what the overall vector is going to be. But the bigger part is this: biphasic, isoelectric QRS is going to start pointing me in the right direction for finding what my true mean QRS is. And there is a reason for it. If any of those other leads, if it is running parallel to the mean QRS, you'll wind up with either a really positive one or a really negative one. But that makes it really, really tough to figure out which one's which. Looking for the isoelectric one's way easier. So in order to do this, we're not only going to be looking at the paper 12 lead, but we're going to be overlapping our information with the hexaxial signal that we talked about from before. This next section we're going to talk about a positive and a negative half. Don't dwell on it too much because it'll make a little bit more sense as we go into later parts. So let's look at this. And this will make sense if you just look at it as a whole. Let's talk about the 2-lead. Everyone knows the 2-lead, right? So this is your hexaxial circle, right? And your 2-lead is this guy right here. And your 2-lead travels at this angle through here. I'm sorry this green's not stepping out as much as I'd like it to. That is the 2-lead. That is the direction it travels. The 2-lead is negative on this end and positive on this end. So, at the halfway mark on this system, you can then assume that the colored in half here is positive and the white part is negative. Simple as that. Now let's take a second and look at the 1-lead, where it's the same idea, that the 1-lead travels this direction, positive here, negative here. So if you divide it in half, this is going to be the positive and this is going to be the negative half, right? Okay, now that we've established that, each of these has a partner lead, or a lead that is perpendicular to it. In the case of the 2-lead, actually let's do this. In the case of the 1-lead, because that goes nice and straight across, right? Which lead is going to be perpendicular or traveling at a right angle to it? And that is going to be your AVF. And so if we then follow down, just follow our red arrow here, and look at our AVF and the fact that it travels this direction and is positive at the bottom and negative at the top, you've got your division right here, and now you know that this is the positive half and this is the negative half. That is all that we're trying to demonstrate here, that there's a positive and a negative side to each one of these leads also that there's these pairings that exist, so that it is 1 and AVF are perpendicular to each other, that you've got 2 and AVL that are perpendicular, and finally you've got 3 and AVR. That's the main point of this. So when you lay all of these out, you actually can start putting a larger picture together. You have your handout, you have your front page, and on there it has this picture. So please see your handout to look at this. In your handout, normal's normal, right? This makes sense. You know, your 2 lead is right here, and so this is what a normal vector should look like, and it should fall within this quadrant on this layout. In fact, normal is even larger than 0 to negative, or 0 to positive 90. Actually, normal is anywhere from negative 29 to positive 100. So I'll just take a notch from here. We'll go just a little bit out from here. And so this is actually what's considered within normal range for things. If you want to look at a true left axis deviation, a true left axis deviation is then this section through here. So left axis deviation is going to be negative 30 to negative 90. And one of the big reasons why we look at this is we're looking for left anterior hemiblock. We will dig into this further later, but I just want to point out that anytime we have a left axis deviation that is between negative 30 and negative 90, we really need to start considering a left anterior hemiblock. Final portion of all of this is going to be the right axis deviation. We'll make him nice maroon. And so that is going to be this section through here. So right axis deviation is from positive 101, I guess, technically speaking, to positive / negative 180. Of course, because this one's on the negative side and this is a positive, so they all wind up here. Those are the rough outlines of what we're looking at when we talk about the mean QRS, because if I find out my mean QRS has a true left axis deviation, I'm going to be looking at different causes compared to a right axis deviation. And in fact, if it falls within the normal range, then I'm going to assume that things are within normal. That's the value of finding the mean QRS and why we're hunting for it. So, step 1 in finding the mean QRS. There's 3 steps total, but this is the first one, and it is super crucial to making things go really well. We're going to get a rough estimate. And that was roughly written, by the way. So in this rough estimate, we're going to focus on 2 very simple things: lead number 1 and AVF. Now, if you also remember, those 2 are perpendicular. So in the case where I'm looking at my 12 lead and the lead 1 and lead AVF are both upright, that will place us in a normal quadrant. And so we can confidently assume that the mean QRS will fall in that same zone. If I wind up having a lead 1 and lead 2, lead 1 and AVF, who are upright and down, so up-down pattern, that will very, very likely mean that the mean QRS is going to be a left axis deviation in this quadrant. It may still be normal, because remember how normal can be as far as -29, but in general, up and down makes me look in this quadrant, or will help me decide that the mean QRS is in that quadrant. And of course, finally, your right deviation is over here. And how do you get a right quadrant deviation? Well, you have negative and positive, or down and up. In extremely rare cases, you can actually wind up with this one here, which is down, down. And this is known as an extreme right deviation, where instead of a normal person or normal heart rhythm where the vector is flowing to the lower right, it is now flipped and it's traveling completely the opposite direction. Big, big heart attacks. That's usually one of your main causes for something like that. For those who like arrows instead of that picture before, and again, this one is from your handout. You'll just want that laying front and center for the rest of the day, because it's going to be pretty necessary to everything that we do from now on. This is just a different layout for those that prefer to see them this way. All right, so step 2 of our QRS estimation. We are fully confident that each 12 lead has one mean QRS. And if there's one mean QRS, that means that there will be an isoelectric lead that is perpendicular. So what we wind up doing is focusing on our 6 frontal plane leads, our 6 limb leads, to try and find where our isoelectric lead is at. Then what's really, really cool is this step here, where we find the isoelectric lead and take that plus the quadrant estimation we did from the previous step, and our mean QRS should fall in that quadrant. So let me show you an example to help put all this together. So QRS example number 1. Step 1, we're going to look at number 1. We're going to look at lead 1 and AVF to determine if they have a positive or negative deflection. So lead 1 is definitely positive, and lead AVF doesn't have a lot to it. I'd almost call it isoelectric, but we'll come back to that part. But it does look like it has a little more of an upward deflection than a down, so we're going to go ahead and call him positive as well. So we're going to go up and up. So if we travel back down here to step 1 and we look at our tiny little dial, or you can look at your handout instead, you will see that up and up puts us in the normal quadrant. So we can confidently assume that our mean QRS is going to be in the normal quadrant. Will be somewhere in the normal. Second step. We're going to try and find the most isoelectric lead that we can. That's going to be one that has an R wave and an S wave that are similar to exactly the same size, and also happen to have the most energy or amplitude compared to the others. So you can see how we have a nice tall R wave here. This one again is positive. This one here is negative. Doesn't even have a R wave at all. This one is really negative because that comes down quite a bit. And this one's quite positive. And then we're back to AVF, which we decided was positive, but honestly, compared to all the other leads you see, this one at least has a positive and a negative, whereas, lead 3 only has negative. So we're going to say that AVF is our isoelectric. So now, step 3. We are going to look for whoever is perpendicular to lead AVF and also happens to be in the normal quadrant. So we're looking for, we're going to do perpendicular and in the normal quadrant. So which lead is perpendicular to AVF? Well, if you look back down here on your hexaxial layout, here in this blue line, not my green line, but the blue line, you'll see lead number, or lead AVF traveling vertically up and down. Who's perpendicular to that? Well, that is lead number 1. AVF and lead 1 are perpendicular to one another. So the final step is to say which quadrant did we decide that the mean QRS should be in? It should be in the normal quadrant. So my lead 1 travels this direction, and this half of it is in the normal quadrant. So we're going to say that our patient's mean QRS is 0 degrees and traveling along lead 1, which makes it normal because it's in between negative 29 degrees and positive 100. All right, next one. Let's do this one in a different color, shall we? Let's do a dark blue. That might stand out. So, step 1. We're going to do lead 1 AVF. So lead 1 has a little up and quite a bit down, so we're going to go ahead and say that one's negative. And then we're going to look at AVF, and we'll say that that's the cutoff between the two leads. And this one's quite a bit more positive than negative, so we'll say that one's up. So if you look at your dial, or your paper, whichever is easier, and this one's up, up, that's not right. And this one's up, down. And here we have what we were looking for, which is down in the one lead and up in the AVF, which gives us a right axis deviation. So we're going to go for right deviation. So my mean QRS should be a right axis deviation of some kind. We just have to pin down what official degrees it is. Because again, it might wind up being just on the edge, maybe in that negative 29 degrees to positive 100. So we're going to keep working on this though. We're not done yet. Number 2. What's step 2? Well, we're going to look for the isoelectric. So which one of these is isoelectric? Well, this one's lead 1 is extremely negative. Lead 2 is pretty well balanced, so he's a little more positive than he is negative, but we'll kind of keep an eye on him. Lead 3 is very positive. Lead AVR, also positive, but pretty well balanced, so we'll put a star next to him. And then AVR is very negative. and AVF is quite positive. So we've got our AVR versus 2 lead, and we have to decide which one of those is the most isoelectric of the two. And the honest answer is AVR, because it has less energy, less amplitude compared to the 2 lead. So AVR. So now for step number 3, where we find who is perpendicular to AVR and is in the right axis deviation. So AVR is this fella right here that travels this direction. So perpendicular to him is going to be lead 3. So we're looking at lead 3. But again, we have to decide, is it going to be a right or a left axis deviation? Well, we know it's a right axis deviation, which means we're going to take lead 3 in the right axis half, or right axis quadrant, and that puts us right here. So we're going to say our mean QRS is a positive 120 degrees, because that's what our numerical marks are throughout here. So 120 degrees. So a true right axis deviation, but we now know how extreme it is. Third example. Let's go orange. We haven't used orange yet. So step 1. Lead 1, AVF. Lead 1 is definitely positive. Oop. We're just going to go, how about this? Let's just do a plain black. Lead 1 is positive for sure. And let's see what AVF has. AVF is definitely negative, so we will do negative here. So on step 1, well, we'll just start up here in the corner, and sure enough, up and down puts us in the left quadrant. So we're looking for a left axis deviation. Step number 2. We're going to find who our isoelectric lead is. So our isoelectric lead, well, we're positive in lead 1. We're mostly negative in lead 2, although it has a pretty low voltage. Lead 3 is definitely negative, so he's off. AVR is also negative, but you know, it's got a pretty low voltage. AVL is very positive, and AVF is negative again. So we're again back down to lead 2 versus AVR and trying to decide which one is the smallest or most isoelectric. And again, it comes down to overall amplitude. And it turns out that AVR has the smaller of the two amplitudes. And I realize this one can probably be argued a little bit, but for intents and purposes, our AVR is the ticket. So now number 3. So we know our mean QRS is a left axis deviation. That was from step 1. But now in step 3, we're going to have to figure out how many degrees it is. So we're looking at AVR, which travels across. Let's do purple. Purple will stand out. This direction. So here's your AVR, which then puts the 3 lead perpendicular to him again. But unlike the last case, we have a left axis deviation this time. So rather than saying the 3 lead for the right quadrant, we're actually going to decide that the mean QRS is or have decided, the mean QRS needs to be in the left quadrant, left axis deviation quadrant. So the portion of the 3 lead that is in the left quadrant is right here. And so you are negative 60 degrees. The other reminder I'll give you with this, because it's a true left axis deviation, we're going to watch out for a left anterior hemiblock. And we'll come back to that a bit later. Wrapping things up, because that's that big question that goes with all of this, is why is it happening in the first place, or what are the causes for it? Well, right axis deviation causes include, well, it's normal for a small population of people, but more often it is the hypertrophy, either ventricular or atrial. That makes sense. More muscle equals increased electricity, hence the more pull that direction. You also have a left posterior hemiblock. Remember, the left bundle branch is split into 2 different parts, left anterior and the left posterior. And so a right axis deviation could be due to this. Finally, you could have just ectopic beats and rhythms that can cause a right axis deviation. But by and large, you're looking at hypertrophy and hemiblocks being likely causes of that right axis deviation. Left axis deviation kind of is the other side of the coin. When do you get a left axis deviation? Well, you get it with a left anterior hemiblock. Ectopic rhythms, of course. The big thing to remember with this, of course, hypertrophy could also cause it, particularly atrial. But left axis deviation isn't considered a problem between 0 and negative 29 degrees, hence the reason we have the negative 29 to positive 100 for normal. So even if you do have a left axis deviation, make sure that it's within that range, and it still may not be an issue. All right, we will pick up with step 4. Thank you very much.